Imagine a place where time itself breaks down, where the familiar rules of reality warp and twist into something else. What if the ticking clock you know, the steady march of seconds, turned traitor, playing by bizarre alien laws? We're not talking sci-fi, we're diving headfirst into the heart of a black hole, a cosmic abyss where the very fabric of space-time unravels. Get ready to witness time grind to a halt, stretch into infinity, and even reverse. What would you experience falling into one of these gravitational monsters? And what would someone see watching you disappear forever? The answers will blow your mind. Time slows down near a black hole due to the extremely strong gravitational field it generates. According to Einstein's theory of general relativity, this phenomenon occurs because the gravity of the black hole curves space-time in a way that affects all measurements of time and space. This effect is known as gravitational time dilation. The mathematics behind this time dilation is described by formulas from general relativity. For example, if you were in a circular orbit around a black hole at radius r, time for you would pass at a rate of the square root of 1 minus 3 gm over rc squared compared to a distant observer. This means that the closer you orbit to a black hole, the slower time passes for you relative to someone far away from the black hole's gravitational influence. As you approach the event horizon, the boundary beyond which nothing can escape, time dilation becomes increasingly extreme. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer, creating some of the most bizarre effects in physics. One of the most mind-bending aspects of black hole physics is how differently time appears depending on your perspective. Let's examine two scenarios that illustrate this stark contrast. If you were to fall into a black hole, from your own perspective, time would continue to flow normally. Your watch would tick at its usual rate, and you wouldn't feel any strange time effects as you cross the event horizon. According to calculations, your journey from the event horizon to the singularity would take a finite amount of time, approximately 1.57 SC divided by c seconds, where SC is the Schwarzschild radius. During your fall, you would theoretically see the universe outside the black hole evolving at an increasingly rapid pace. Stars might appear to age quickly, galaxies evolve in fast forward, and you might witness the distant future of the universe unfold before your eyes. From the perspective of someone watching from a safe distance, the experience is dramatically different. If you were observing a friend falling into a black hole, you would see them move progressively slower as they approach the event horizon. Their clock would appear to tick increasingly slowly, and their movements would seem to freeze. The light emitted from your friend would become increasingly red-shifted, stretched to longer wavelengths, making them appear dimmer and redder, until they eventually fade from view. Remarkably, you would never actually see them cross the event horizon. It would appear to take an infinite amount of time from your perspective. Their image would hover near the horizon, growing fainter until it becomes indistinguishable from background radiation. This strange freeze-frame effect is not just theoretical speculation. It's a direct consequence of how light behaves in the severely curved space-time near a black hole. While your friend experiences a normal passage of time and crosses the horizon in a finite period by their clock, the light signals carrying that information take longer and longer to escape the intense gravitational well as they get closer to the horizon. What happens if we could somehow measure time beyond the event horizon? According to general relativity, something truly extraordinary occurs inside a black hole. The roles of space and time become reversed. Outside a black hole, we experience 3 dimensions of space and 1 dimension of time, allowing us freedom to move in any spatial direction but only forward in time. However, once you cross the event horizon, the mathematics indicates that what was once the radial dimension of space, the direction toward or away from the center of the black hole, becomes time-like, and what was once time becomes a spatial dimension. This means that inside a black hole, time can theoretically move forward, backward, or even stand still, while movement in the radial space dimension must progress forward just like time did outside the event horizon. The singularity at the center of the black hole is no longer a place in space, but an inevitable moment in your future, an event that cannot be avoided, just as we cannot avoid moving forward in time in our normal experience. This role reversal creates a completely new space-time dimension inside the event horizon, where the conventional rules of physics as we know them break down. It's as if you've entered an entirely different universe with its own bizarre laws. While we cannot directly experiment with black holes, several thought experiments help us explore these concepts. The interstellar scenario. In the film Interstellar, astronauts visit a planet in close orbit around a supermassive black hole. Due to extreme time dilation, 1 hour on the planet equates to 7 years passing on their mothership and back on Earth. While dramatized for the film, this scenario illustrates a legitimate consequence of Einstein's equations. A spacecraft orbiting close to a black hole's event horizon would experience time much more slowly than objects farther away. The Hayden Preskill thought experiment explores how information thrown into a black hole might be retrieved from its Hawking radiation. In this scenario, Alice throws a quantum state into a black hole that is entangled with Bob's quantum computer. Surprisingly, theory suggests the black hole acts like a quantum information mirror, scrambling and almost instantly when measured against the black hole's lifetime. Another fascinating thought experiment involves trying to measure the one-way speed of light by placing a clock at the event horizon and sending light pulses tangent to it. The light would travel around the curved spacetime and return to the clock. This could theoretically allow measurement of the one-way speed of light, though implementing such an experiment remains beyond our current capabilities. An intriguing question is whether time near black holes follows the same arrow as elsewhere in the universe. A study by scientists at Leiden University used computer simulations of 3 interacting black holes to examine time's reversibility. They found that even when running their simulations backward in time, about 5% of scenarios didn't return to their original conditions. This broken symmetry hints at a fundamental irreversibility in spacetime, suggesting that even near black holes, time may have a preferred direction, flowing from past to future in ways that cannot be reversed. The extreme time effects around black holes have profound implications for our understanding of physics. Black holes represent natural laboratories where we can test our theories of gravity and quantum mechanics in extreme conditions. The study of time near black holes has led to important developments in theoretical physics, including black hole thermodynamics and the holographic principle. Black holes also raise fundamental questions about information preservation and the ultimate fate of matter. When something falls into a black hole, the information about its quantum state appears to be lost from our universe, creating the famous black hole information paradox that continues to challenge our understanding of physics. Conclusion. What if time on a black hole measured differently? The fascinating answer is that it already does, in ways far more profound and bizarre than our everyday intuition suggests.